Welcome back to my channel.
Bing! That was not very enthusiastic, Hugo. Carly's late today, so she's not here to do our intro. So that'll be a $10 fine for her. We are moving on to Unit 7. So if you didn't take your Unit 6 exam, you need to be doing that pronto. We are moving on to the exponentials and logarithms unit. This unit is like 10 years long. So, we're going to be in this unit for a while. And this is the first, this is really the first stuff that we're doing this year that doesn't have some element of review. Like a lot of the stuff that you're going to see in this unit is or should be new stuff. So we are going to remind ourselves what exponential growth and decay looks like, and then we are going to talk about this new thing called the natural base. So we're starting on page 76. And we're actually not going to fill in every single little thing on this paper. We're only going to fill in the important parts. So back in 9th grade, I think that was the first time that you were introduced to exponential functions. So exponential functions look like this. They look like y equals a times bx. So this is our starting point. So let me show you a few on Desmos before we get going too far in this lesson. So I'm just going to type in a few exponential functions so you get a picture of them. So let's do an easy one. Let's do like 2 to the x. So one thing to notice here is what this graph looks like. He's like a flat line that shoots up really high. Okay, let's change some numbers. What if this were a 10 instead of a 2? Did he change by very much? No. Let me show you again. Okay, watch when I change him to a 10. He doesn't change by very much at all. Well, I can put a letter on the front of this, so maybe I should do like a 5 times. That didn't change him very much. So the biggest takeaway from this is that they all kind of look the same. I'll do a fraction this time. That didn't really change him either. So they all kind of look like this picture that you see here on your graph. They start out really flat, and then all of a sudden it explodes and the numbers become really big. So this is what an exponential function looks like. This is what most of the graphs look like. This year, we are going to refer to these functions as exponential growth or exponential decay, because we're going to look at some word problems associated with this function. So this little box here says you will see this function formula written with different letters, but it is the place that the letter is in that is important, not the letter. So we're not going to get so focused on that this should be A and this should be B. What we want to pay more attention to is there a number in the front, and what is our base number? You're hanging in? Okay, the number in the position A is your y-intercept. The number in position A is your y-intercept. That is where your exponential graph passes through the y-axis. So let me show you in our Desmos what that would look like. So I'm going to change this back to 2 because that's the most basic. And I'll put number on the front to be 2. Notice that he passes through at 2. What if I change it to -2? Now he passes through -2. What if I put 7? He's going through the y-axis at 7. So whatever number you put on the front here in this A position, that is where your graph will pass through the y-axis. So that's your y-intercept. Your B is your growth or decay factor. So this is by how much your function is growing by or by how much it's shrinking by. And then lastly, whatever is in the x position is always time. So when we're looking at basic functions, we're not paying so much attention to growth and decay factor and time. But as soon as we get into the real world problems, these positions will matter a lot more. So A is where you're passing through the y-intercept. B is how fast you're growing or shrinking. And X is your time. So now we have 2 examples. We have one of exponential growth and one of exponential decay. And I think that it would be helpful to look at them together before we separate them out. So I'm going to highlight them and then talk about some of the differences in how they look. They really should have arrows at the ends. If you're not going to highlight yours, that's fine, but put arrows at the end, that may help. Before I forget, I need to empty my recordings. So sorry. Delete. Okay, back to business. So notice that exponential growth starts down here by the x-axis and shoots up. So this part of your graph is going up. That's why it's exponential growth, because you start down here towards 0 and then you shoot up really, really quickly. This guy is exponential decay because he's going downward. So he decreases very quickly at first and then kind of evens out towards 0. So the biggest difference between exponential growth and exponential decay is that this guy starts around 0 and stays there for a while, then shoots up all of a sudden. And this guy decreases very quickly, and then once it gets towards 0, starts to slow down and stay at 0 for a while. You're okay? Okay. So this is an example of the function y equals 2 to the x. Y equals 2 to the x. So I'm going to write that out here a little bit bigger just for our reference. And we'll look at the things that we talked about over here and make sure that they're true. So the number on the front is supposed to be my y-intercept. I don't really see a number here. So that means that the number that's hanging out on the front is a 1. This is really 1 times 2 to the x. Well, then that means that our y-intercept should be 1. And if you look at your graph, your y-intercept is at 1. It's at 0, 1. This graph passes through at 0, 1. This guy is your growth factor. This guy is your growth factor. What this 2 means is that your function is doubling over time. It's doubling. So if you start with 3, it goes to 6, and then 12, and then 24. Every single time, it doubles itself. That's why it grows so quickly. If you start with 1, it doubles to 2, 4, 8, 16, and by the time you know it, you're like at 496. So here, our growth factor's 2, and that means that we're doubling. Our number is doubling every time. Then the last thing that we're going to be asked about on our quiz today is what is the domain and the range. So domain we've talked about quite a bit. Remember, when we're talking about domain, we are talking about what can the x values be. So I'm going to remind myself with like this line that domain is saying what can my x values be. Now you don't have to write that in unless that's going to be a helpful reminder to you. The domain is why I had you guys write these arrows. Because when we talked about domain, we talked about how you want to look at, is there a restriction on what your x value can be in the negative direction? And the answer is no, because you have an arrow here. So this graph is coming from negative infinity. And if we let it go on forever, it will go to infinity. Which means that for this graph, your domain is all reals. There is no restriction on your domain. You can plug in any value that you want for x and get a value out. Range is the one that is special. So range is your y values. So we're looking at how high and how low can your numbers be, or are your numbers. So these, when we talk about range, we're talking about your y values. So underneath here, I'm just going to ask myself, what is my max and what is my min? What is my max? What is my min? So my max hopefully is easy for you guys to see. The maximum value that this graph can be is infinity, because this arrow is pointing up and to the right. It can just keep going on forever. So the maximum of this graph would be infinity. The minimum of this graph is where it gets interesting. So let's look. Does our graph cross over into the negative side? No. This graph never crosses over into the negative side. In fact, if I went out to this problem and I just kept zooming out as far as I can go, so my x scale is changing. Now I'm all the way at 10,000 and 15,000 and negative 20,000, but it never crosses through and turns negative. So that means that our minimum is around 0. It's not ever going to cross over into the negative. In fact, it has a fence at 0. And when you have a fence, the fancy word for that is asymptote. We looked at that a couple lessons back where if we graphed something, we might run into an asymptote, and that is a fence that your function can be next to, but it will never touch. So your range is any y value greater than 0. It can't be 0. It can't be 0 because you have a fence at 0. It can be any number, though, above 0. You're hanging in? Okay, decay is going to be very similar then. Just a few things change. So let's look at this function. I'm going to write it a little bit bigger again just so that I can make things as clear as possible. This time, once again, what we have in the front is a 1. So that means that your y-intercept is at 1. So that didn't change. Between growth and decay, that didn't change. Our y-intercept was 1. This guy, though, should say decay factor. This guy should say decay. What is our decay factor? Well, in this case, we are cutting our population in half. So we're halving. That's a weird word. Halving. You can write halving if that makes more sense to you. But it's really that word. So what does this mean? This means that if you start out with 1,000, then it cuts itself down into 500, then 250, 125, 70, 62.5, 31.25. It cuts itself in half every single time. That's why it's decreasing so dramatically. Because at the first time, you go from 500 to 250. That's a big drop. So this time, our decay factor is 1/2. Domain, well, the graph is going in a different direction, like it's starting up high and coming down low, but the arrows are similar. There's an arrow on this end and an arrow on this end, so domain, once again, is all RILs. You'll find that for almost any exponential function, your domain is all RILs. Your range, now even though it's on a different side, like this, on this side, the graph is on the negatives, and on this one, your graph is on the positives, it has the same range. Your range is still any number bigger than 0. That fence is still at 0, the graph is just at a different part of the fence. So this is our basics of exponential growth and decay. Growth starts out small and then gets really big really fast. Decay starts out big and then starts to get small. Well, actually it starts out big, gets small really fast, and then stays around 0 for a long time. So how is this related to what we're actually talking about in this unit? Well, we are now going to change this letter B to the natural base. That natural base is this little letter E. So our blanks for this are, in real life, things grow continuously. In real life, things grow continuously. Meaning that when you're a little kid, it's not like you wake up one day and you've grown a foot. You grow over time. It's a gradual process. That's what they mean by most things in life grow continuously. So this says, for an example, an infant will continue to grow over a year period. The baby doesn't just double in size on its first birthday. The natural base, letter E, is used when modeling continuous growth that occurs naturally. And hopefully some of you guys have seen this in science before, because things that grow naturally are populations, bacteria, radioactive decay. In our case, in the math-related fields, it's money. So it's finance, it's accounting. E represents how fast you could possibly grow using a continuous process. So notice how similar it is to the last function. The only difference is in the parentheses is the letter E, and it will always be E. So the natural base in this little box is irrational. And he actually stands for a number. The letter E is a number like pi. So I'm going to plug him into my calculator so you guys can see what number he really is. He looks like this and goes on forever. If I plugged him into my iPhone, I would get even more digits than that. So we're going to write here those digits. E is the number 2.7, 18, 28, 18, 28, 45, ... And those dots mean that number is going to go on forever. So it's like pi. Pi is 3.14 and goes on forever. The letter E, the natural base, is 2.7 and goes on forever. Well, if we want to look at these positions, they're basically the same. In the last example, it was y-intercept, and that's still true. It's still the y-intercept, but in problems in real life problems, we refer to it as the initial amount. So if we're talking about populations, we're talking about the initial amount of people. If we're talking about money, we're talking about the initial amount that you deposit. E is still your growth or decay factor. We just know what it is now. It's the natural base. It's 2.7. So E is still how fast it's growing or decaying, but this time we know that that value will always be 2.7. And X is the same. It's still time. Just like before, these descriptions don't become super important until we get to this next page, where all of a sudden we're doing a bunch of word problems. Okay, well, let's look at what the growth and decay looks like. Well, these look almost exactly the same as the last graphs. So notice this starts out slow, starts out towards 0, and then gets really big all of a sudden. So this is an example of growth. And this is the function y equals e to the x. On this side, we have decay. And this is the function y equals e to the negative x. Starts out really big, gets small very quickly, and then tapers off to 0. What is the only difference between these two things? There's one difference between this function and this function. The negative exponent. This is what tells you if something is growth or decay. If your x is positive, you would say that it is growth. And if your x is negative, you would say that it is decay. It doesn't matter what kind of number it is. So it could be negative 1/2 x, and that is decay. It could be 1/2 x, that would be growth. It could be 5x, that would be growth. The only thing that matters is the symbol. So now that we know that, let's jump all the way to the bottom of the page. And you guys decide, just using that as your criteria, whether or not the exponent is positive or negative, and write a D or a G next to each one for growth or decay. Looking good. Okay, let's check. 1 is decay. 2 is growth. Decay, growth, decay, decay, growth, 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 growth. How'd you guys do? Did you do okay? Okay, so now we only have one more element. We only have one more element on these natural base exponentials. It is very similar to what we did on the last problem. So what we want to focus on these problems is the y-intercept, the domain, and the range. So the first thing it wants you to do is match the function with the graph. And then after we have them matched, we'll decide on the domain and range. On this guy, your y-intercept should be at 4. Your y-intercept is at 0, 4. Now this guy, I don't know what happened here, but this should be at 4. So A should be 4. So it could be A, it could be B, because that guy's going through 4 like it should. It cannot be C, because C goes through 2. So now between A and B, which one is it? I don't know. But one of them needs to start high and go low. Do you see what I'm saying? Shizzlenits. Maybe we need to graph them. I'll graph them. I went over this before class, family. Y equals 4 times e to the x. Okay, so that one looks like this. So he matches B. Is that true? Yes, no? Yes. Okay, so let's write that down. And he is going through 0, 4. Okay. Well, shouldn't this one be going the opposite way? Sorry. So I think these notes are wrong because this one is supposed to look like this. Do you know what I'm saying? Because he's decay. And if this is the X and Y axis, he should be going through 0, 4. So let me double check using Desmos that I'm not lying to you. So he is 4e to the negative x, and then we minus 2. What is that? Oh boy. I know what happened here. Nope. Okay, I remember. So at least we feel good about number 1, right? Yes? I think number 1 should be a yes, because he's just 4e to the x, and he really is going through 0, 4. So we should feel okay about number 1, that he really does match letter B. Are you okay there? Okay, here's what happened on the next one. He should have gone through 0, 4. So this means your y-intercept is at 0, 4. But then this minus 2 means you shifted him down by 2. I should have remembered that from our functions family situation. This guy means shift down by 2. So if he starts at 0, 4, and we shift him down by 2, that means his new y-intercept is at 0, 2, and he's letter C. And now that makes more sense because letter C is decay. So let me show you what that really looks like in Desmos. So here it is looking negative, and it is going through 0, 4. But then I'm going to add on that minus 2, and he shifted down to 2. Is that making a little bit of sense? Are you sure? Okay. So then it looks like we're going to have to do the same here. This y-intercept is at 1/2 or 0.5. But then this guy means shift up by 4. This guy means shift up by 4. So we start at 0.5 and then we shift up 4. So that's why this guy is at 4.5. So this one is A. And now that makes sense because it is also growth. That is also growth. So if we have to match the graph, we have 2 options. We can just plug it into Desmos and figure out which one goes where, or you can look at the y-intercept and then see if you shifted it up or down. Okay, domain. Well, all of these are very similar with their domain. In fact, they're all the same. All of these domains are all reals. So domain on these problems should be fairly easy in quotation marks because your domain basically is all reals for every problem. And the only thing that's different is your range. Luckily, the range is easy to find. So for this problem, B, for this problem B, your range is any number greater than 0. Notice your fence is at 0. So y can be any number greater than 0. I'm going to write that down. Because the fence is at 0. Okay, well this one is the next easiest one for me to see. This is y can be any number greater than -2. His fence is at -2. And then this one has a fence at 4. So I'm just looking to see where that line starts to flatten out. Okay, well now let's match them up. This one that's greater than 4 matches this one. And look what I have highlighted, +4. Y can be any number greater than 4. And this one matches this guy. Y can be any number greater than -2. Notice the shift matches. Y can be any number greater than -2. And now this one matches because I didn't add or subtract anything. So y can be any number greater than 0. It turns out if you shift up or down, your range matches that number. So when I shifted down by 2, my range is y is any number greater than -2. When I shifted up by 4, my range changed to any number greater than 4. So whatever you add or subtract moves your fence to that number. Okay, so the biggest takeaways then from this page, because our quiz is on this page, can we recognize growth or decay? And the only thing that you need to look at for that is the sign. And then the next one is, can you identify, I think they only ask about range and domain. So really, you would just need to pay attention to if they add or subtract anything to answer those questions. Okay, so let's have you try your quiz. It's only 6 problems, and as you have questions, I'll just be walking around to answer any questions that you have. Okay? Okay.